All right, let's jump right into this explainer and become visual detectives. Have you ever actually stopped to look around and wonder how stuff fundamentally changes? I mean, we're surrounded by constant change, but not all changes are created equal. Today, we're going to decode the secret language of matter and visually track exactly what happens when substances undergo a true chemical transformation. So let's kick things off with a real mystery. What is actually happening down at the microscopic level when an object permanently changes into something else? When a piece of wood turns to ash, or a shiny nail turns to rust, reality as we know it for that object has fundamentally shifted. It's not just a wardrobe change, it's a total identity change. So what exactly is the microscopic trigger for this? Well, Prep Scholar hits the nail on the head here. The golden rule of our investigation is this. A true chemical change only happens when a substance's molecular bonds are broken and snapped back together in a completely new way. If the molecules remain exactly the same from start to finish, you haven't witnessed a chemical change. The atoms literally have to be taken apart and recombined. That brings us to Section 1, Physical versus Chemical Changes. To spot the real deal, we first need to weed out the imposters, those mere physical changes. Just look at the contrast in energy and reversibility here. Melting ice cream, that's just a physical change. Its molecular structure hasn't changed at all, and you could just pop it right back in the freezer. But burning logs? No way. That takes a massive amount of energy to break those strong molecular bonds, rearranging them into completely irreversible, entirely new substances like ash and carbon dioxide. You simply can't unburn a log. Okay, let's test this logic for a second. Ask yourself, if you accidentally drop a glass on the kitchen floor and it shatters into a million tiny pieces, did we just witness a chemical reaction? I mean, it certainly looks completely different, and it's pretty hard to put back together, right? Actually, the answer is absolutely not. While physical energy was used to break the glass, zero energy was used to rearrange the molecules themselves. The pieces of glass on the floor are the exact same glass molecules that were in your hand a second ago. It's just a change in size and shape, making it purely a physical change. Which leads right into Section 2, spotting the visual evidence. Since we obviously can't see individual molecules with our naked eye, what kind of macroscopic clues can we look for to prove a reaction is actually happening? Well, LibreText gives us this fantastic 7-point checklist for visually confirming that a chemical reaction is taking place right in front of you. If you see a sudden, unexpected change in color, or violently bubbling gas, or maybe a radical shift in temperature, like something suddenly getting intensely hot or freezing cold, you're likely witnessing molecules being torn apart and rebuilt. Light being produced, or a solid precipitate suddenly forming out of a clear liquid, those are total dead giveaways. Now for Section 3, the frame-by-frame simulation. You want me to show you a chemical change through video? Let's simulate exactly that using a classic Inquiry Lab experiment. We're going to slow down the conceptual tape of a reaction, frame by frame, and watch the mechanics of molecular rearrangement in real time. Okay, frame 1, we add iodine to water, which gives it this subtle yellow-orange tint. Frame 2, we stir in some cornstarch and boom, an immediate chemical indicator. The liquid violently shifts to a dark blue-black color, proving a new substance just formed. Frame 3, we drop in a crushed vitamin C tablet. And frame 4, the grand finale, as we stir, that dark color vanishes completely and bubbles vigorously start to form. By simply mixing these normal household items, we get a dynamic real-time show of two major chemical indicators, extreme color change and the rapid evolution of a gas. We literally just watched molecules rearrange themselves. All right, Section 4, types of chemical reactions. Because just like movies have different genres, these reactions have different profiles. Not all molecular changes are the same, so let's categorize them. First up is combustion, probably the most dramatic genre. This is what happens when substances react aggressively with oxygen. Think about mixing a hydrocarbon like methane with oxygen to create carbon dioxide and water. The breaking of those initial bonds releases massive amounts of energy, which we see as heat and light. So whether it's a slow-burning match or huge firework exploding in the sky, that's combustion. Then we have decomposition. This is exactly what it sounds like, things breaking down. But it usually needs a push, like heat or electricity. A perfect example is passing an electric current through plain old water. That electricity violently forces the H2O molecules to break down into pure, separate hydrogen and oxygen elements. You're starting with one complex thing and forcibly tearing it into simpler pieces.
Going in the exact opposite direction, we have combination, or synthesis. This is where you take two simple substances and fuse them into one entirely new compound. For instance, when iron is exposed to oxygen, they synthesize to create iron oxide. We commonly call that completely new molecule rust.
And finally, we have replacement reactions. Think of this as a highly dynamic molecular dance where partners are actively trading places. In a single replacement reaction, one element just swaps out with another in a compound. But in a double replacement reaction, two different compounds actually trade their ions with each other to form two entirely new products. It's this constant, fascinating exchange of atomic partners. Moving to our final part, Section 5, Everyday Real-World Chemistry. Because honestly, you don't need a white coat and safety goggles to witness these changes. They're happening around us all the time. Your kitchen is basically a massive chemistry set. When you bake a cake, you're combining wet dough and applying heat, an endothermic reaction, to create irreversible molecular changes that result in a fluffy, delicious dessert. Frying an egg, the heat changes the proteins in the egg white from clear and runny to white and solid. That's a textbook chemical change, happening right in your frying pan. And remember those color changes we talked about earlier? Think about a banana sitting on your counter, turning brown as new, darker substances with a completely different taste begin to form. Or consider cooking a steak. That familiar red to brown color change in your cooking meat isn't just it getting hot. It's actually a sign of the iron in the meat's myoglobin oxidizing on a molecular level. It's literally high-level chemistry in action on your dinner plate. So let me leave you with this final thought. Think about the last meal you ate. The very second that food hit your mouth, your saliva introduced an enzyme called amylase to the sugars, kicking off a massive chain reaction. Your own digestion and metabolism are non-stop dynamic chemical changes happening every single second of your life. Your body is the ultimate chemistry lab. So the next time you see a rusty nail, a baking cake, or even just take a breath, I challenge you to look closer. What molecules are shifting right in front of your eyes? Keep observing, keep questioning, and I'll see you in the next explainer.